We're going over chapter 8. So before we get started, let's actually learn how to draw this. So as you remember from the professor's drawing, so we have to first draw a center line. So let's draw a center line. Okay, center line. Okay. Then we draw a circle. This is our starting, and we draw the same size circle. Okay. Alright, cool. Okay, then we draw, oh, this is not a full circle. Let's see if I can draw a half one. Okay. Move this here. Okay, I'm gonna obviously get rid of this partially. Partial. So there we go. Okay, then we draw a whole line through this, and we shade this. Then again, shade this. Then we draw another circle down below the other center line. So let's draw it here. And I'm guessing we're supposed to draw a center line, so from here to here, and then here, and it starts again. Keeps going down. So what you'll notice is that you have a center line between each. So you'll have a center line here. Keep going. And then you'll have a center line here. Keep going. And then you'll have a center line here. Here. So just imagine this as like one, like these lines. Just imagine these lines. So then from here, same thing. Then we go all the way across. Okay. So then our next one is going to be just after the center line here. So it will be here. So if I can draw the circle. Alright, okay. I'm gonna just Control C, Control V this because I can here. Then the next one will be just below this. And then the next one will be around here. Then the next one will be Control Z, Control V. And let's move this just above this. Is that correct? And it should be here. Yeah. Right below. Okay. Alright, yeah, and then we just follow this back here. Alright, then we just draw the lines. So over here, over here. Then we draw another two lines here. Another two lines here. And then we finish off with this. And then from here to here, we have this one here. This one here. Imagine this is the same thing. Then just shade it, shade it, shade it. And there is your mechanical spring. Okay. So I just wanted to quickly go over this before we start how the spring that we need to be able to draw these. Alright, let's go back to our spring section. Alright, so what do we have here? We have over here mechanical springs. So springs are elastic devices that store and release mechanical energy. They play, yeah, we know the introduction. What do we know about spring? Why do we need spring? Can you draw a spring? We could not in the lecture, but that's fine now. Part A. So part A, generality terminology. So a spring is an elastic flexible element that deforms under an action of an external load. When deforming, the spring stores potential energy. Okay, that's fine. Spring undergoes significant deformation when loaded. Their compliance enables them to store readily recoverable mechanical energy. So now, that word there, recoverable, I did not know they also do this. So because I didn't know this, I'm going to now just quickly write that down. So springs undergo deformation under load, and then from there, what happens then? Their compliance. So I'm saying their ability to do this, to do this, allows them to store. And I'm gonna use caps lock, readily recoverable mechanical energy. Okay. I don't know about the recoverable part, so that's interesting. All right. So types of springs, they can come in many shape sizes. So typical use. Now this is important, so I'm just gonna quickly jot it down here. Let's change the font. All right. So we got uses of springs, and we got change this back to black. All right. So we got shock absorption. So shock absorption, that's vibration. Then you got vibration damping, energy storage. Now the last, I don't know about this measurement device. I know about transmit forces because that we have F equals kx. When we get the measurements devices back, I will add on because I don't know what this is. So absorbing impact shocks, cushioning vibration. So we have a suspension system, I'm guessing. Then clutch disc torsion springs. So when clutches engage, the contacts is established between the engine and the transmission. These springs help dampen and absorb the rotational shocks. Okay, interesting. So for this, we have clutch. The example is so EX, EEG. We have clutch disc torsion spring. So they absorb. Now this is clutch disc. Okay, no, that's enough. All right. Motion control. Typical use is motion control. So maintaining contact between two surfaces is this one over here, measurement device. Okay, what's maintaining contact between two surfaces? So this is not okay. This is the applying forces. So I get this part. This is this one. So for example, anything adjustable usually has a spring. So that's not an issue. Return a mechanism to its default position. Okay, so these things are not mentioned here. So let's add this. Let's go back first here. Motion control. Okay, so motion control. I'm gonna actually write this in red because this is in the slide, but it wasn't given earlier. So motion control. So for example, I think this is when you have a camshaft and you're trying to go back to the original position. I think we're just gonna write motion control. So revert back. No, not revert back. This is just maintaining contact. Maintaining contact. So something like rotating a camshaft. Okay. Typical use of a spring, applying forces, return a mechanism to its default position. Okay. So returning default position, and this in this example we're using torsion plus a return springs. So return springs. Okay. Anything else? Yeah, we talked about storage. So okay, we talked about this. To measure forces. Okay, what's this? Linear springs exhibit a behavior. Oh, so like a Newton meter is proportional to an applied force. Such springs can be calibrated and used to measure forces. Yeah. So basically, I'm just gonna write over here. Okay, now I understand that part. So I'm gonna go in black. So we have was it measurement device. So this is basically use Newton meter to measure forces, which makes sense because it's calibrated using spring. Okay. Oh, that's part A done. Okay, nice, very nice, very nice. So very straightforward. Let's go to part B now. So types of springs. So we have linear springs and torsion springs. Okay, so we have a linear spring. So let's write linear spring over here. Okay, so we have types of spring. Let's do Actually, let's do it like this. Change this to a header. We have part A, part B, part B. Types of spring. All right, cool. So we have two types. So we have linear, but I do not want it in header 2. Let's make a header 3 linear. And we also have a torsion. Now with this, you have, I'm gonna draw them so I remember. So you have your typical springs. And the torsions you have, they are coiled up and they're a bit different. So I'm gonna just over here. And, okay, I'll get the idea. And this is F equals Kx, and this is M equal. Okay, I cannot type. Right. So F equals Kx, M equals Kt theta. Okay. Type spring, the simplest spring is the tension bar. This is an efficient energy store since all elements of stress are identical, but deformation is small if it's made out of metal. So the bicycle wheel spokes are the only typical application when it comes to mind. So we have a tension bar. Okay, that's interesting. So we can just right here, over here we have a tension. Oh no, here we go. Oh no, we're trying to type here. Tension bar. Okay, let's write in body now. So this is, so the only thing that comes to mind is bicycle wheel spokes. So are these, yeah, these are these things over here, right? Okay, so these are bicycle wheel spokes. And that's it. So let's just make a quick yoink. Let's add this over here. Okay, so we're looking at, obviously, let's just add a red icon and we're talking about this. All right, that's a cool transition there. All right, type springs. We have some formulas here. We have Hooke's law. We got the stress is elastic Young modulus times E. Okay, so from this, all we need to know is that we have a spring or a tension bar, right? And then from there, what's happening to the tension bar? Okay. Okay. All right. L delta L. We got area of this, and then we got the force is acting here, and then from there all we need to know is that the K is equal to F, not F, the K, this is my force F, this is K is equal to EA over L, and this is the effective spring constant. All right, effective spring constant. All right, cool. Beam from the sense of many springs, deflection, static deflection, load F, and the end cantilever beam can be appreciable. It depends on the cantilever geometry and the elastic module. Unlike the constant cross-section beam, the leaf spring is stressed almost constantly along the length because the linear increase. Okay. This is just beam formula. This most likely will be given to us. I don't think we'll have to memorize this, so this is not an issue. We have a leaf spring. So, okay, what's so special about a leaf spring? Okay, I think we just need to know it. I don't think we need to know any more details about the spring. So I'm guessing a short summary. Let's just write a short summary here. So leaf spring. So another type is leaf spring. And we're just gonna put a picture here of this icon here, and this is a leaf spring. Bam. Okay, now this is important. This is when we have helical springs. So we have helical compression and helical tension. So this is helical compression in A and helical tension. So I'm guessing we have the hook here so we can uh, hook it and then it can be under tension. So okay, so most common is helical compression. Shortcut of most metal is to rely on bending and torsion. The wire of helical compression is loaded mainly in torsion, therefore use usually circular cross section. This type is the most common, so we shall focus on it. So we're going to just subdivide it. So let's just subdivide it here. So body header 3 helical springs, and under thing we have helical compression and helical tension. So this is most common. So common. Okay. Now with this, we're just gonna quickly yoink this this one here. Okay, copy this here. This is this. I'm gonna quickly copy this one here as well, and this one will be for here, and then we're gonna specify it. So gonna use our trusty pen here. Okay, so we have our helical tension one here and helical compression here. Okay, so we're focusing mostly on helical compression. Let's go over it. Helical compression types of springs. So what's so special about them? They are mainly in torsion. So these things are loaded. Oh, okay, hold on. Let me bring this back here. Yeah, so they're mainly loaded in torsion, and they usually have a circular cross section. Alright, cool. Okay, let's go on to helical tension. So extension spring is similar to compression spring. However, it requires special end. So this is a special end. A tension spring can be wound with initial preload so that it deforms only after the load reaches a minimum value. So this usually has a preload. And why is that important? So that it can only deform after min value. Okay. Helical tension. So this, yeah, helical tension. So this is just what it looks like. Okay. Special spring, rectangular sections, bevel washers. So a disc bevel washer is disc is a washer manufactured to a conical surface. So this over here, bevel washer characterized by short axial lengths and relatively small deformations, and often used in stacks as well. So their geometry can be engineered to produce highly non-linear characteristics. Okay, parallel stack, series stack, and series parallel stacks. Okay, let's go back to the rectangular sections. I'm just gonna mention them quickly. So let's go back here. Okay, so we also have rectangular sections. These are special springs. Okay, and I'm guessing it's to do with how they're made. So I'm just gonna quickly just take a picture of this, paste it here. This is our rectangular, and we're gonna put nice okay, rectangular section. This special type of spring. Then we have bevel washer. It's a disc spring manufactured to a conical surface. So now we have a bevel washer. So let's do it here. Bevel washer. Alright. Oh, not bevel, sorry. Belleville washer. washer. All right, cool. Let's go caption. So we have smaller font. So this is a disc spring, which is a washer that is manufactured to a, so control V, conical surface. Okay. What else? They're characterized by short axial lengths, and this is so small deformations, and are used and used in stacks. All right, cool. So that's the short thing, and what happens to them? They highly non-linear characteristics. All right, that's it. Let's go up. Okay, let's quickly give some examples. So let's just add on here. Let's go here. So this is our bevel washer. All right, and then they're often used in different spray. Oh, I think, did we miss something? Hold on. No, not yet. We didn't miss anything yet. So parallel stack, series stack, and so I'm gonna just yoink all of them. So okay, let's go, and for this, let's see if I can fit them. So this can be this can be a bit larger. All right, I think that works. And maybe I can move this here, and then I can move this on top. Yeah, that works. Okay, there we go. This is our bevel washer here. Okay, and maybe move this to the side. All right, cool. That's bevel washer done. So you have torsional bars. So they're rotary spring that involve torque and angular deflection. The simplest of these are the torsion bar, which are loading is pure torque. So torsion bar, their only loading is rotation. Okay. They're stiff compared to other forms of rotary spring. However, they do have many practical application in vehicle suspension. So they are used. So torsion bar is used. So the key thing about torsion bar is, so let's mention it. So let's make header 3. So torsion bar. So what are they? They are, let's do body. No, let's do caption. So they are rotary. No, let's do here. They are rotary. No. Caption. Rotary springs, which have only torque. Oh, what was that? Hold on. Let's go back. All right, let's go and close this. Which only have torque loading. All right, cool. What are they? They're also are stiff compared to other rotary springs. Okay, and we have a quick picture of this, and we're gonna paste it here, and yeah, we're done for torsion bars. All right, cool. Okay, next we have so this is torsion bar. Now we have torsion springs. So we have torsion spring, spiral torsion spring. Okay, let's just quickly load that up. Conical, so I'm guessing this is still torsion, right? Volute spring. So all these are different type of springs and their usage. And okay, so this is a lot of usage. Will we be asked about these? Not sure, to be honest. We might be asked. Okay, so how about we just add the ones we can think are relevant. So we had torsion bar. Now we're just gonna copy this. Control C. No, Just add another over here. And we have, instead of torsion bar, we have torsion spring. I think we just need to know how it looks like, maybe. So let's have a torsion spring. So let's just quickly add this over here. Control V. Done. Bam. Next, we have a spiral torsion spring. So let's put it here, and this is boom. Let's add this one here. So boom. So let's add this here. Okay. Then what's next? Conical springs. I mean, that's in the name. Let's move this across. Conical. All right, cool. We have conical. So conical spring right here. Maybe make it a better one. Conical. There we go. Conical spring. Okay, so we have conical, we have low, we have diameter, and we have small d for the, I'm guessing the diameter of the material that the spring material here. The coil. Sorry, the coil. Volute spring, that's interesting. So these look like some sort of scissors here, or some sort of chopping mechanism. And this is a volute spring. Okay, interesting. So let's do the same thing here. So let's add volute. And let's just quickly make a picture of this. There we go. A volute spring. I mean, there's a high chance we will be asked about the uses of these things, so we're just writing them down, and then we can add on to these diagrams. Okay, let's look. So compression coil, extension coil, torsion leaf spring, torsion bar, flat spring, constant force spring, bevel washer, a gas spring, volley spring, wave spring. Okay, let's add the things that we do know. So this is for a volute spring. Let's add a caption. So they're used in, let's say, recoil systems. There we go. Done. What about torsions or spiral torsion? Is there anything for spiral torsion? What's a gas spring? Hold on. Gas spring. Images. Okay, we didn't learn gas spring. Wave spring. What's that? Wave spring. What's a wave spring? Okay, so a wave spring is something like this. So let's add this here. This is a wave spring. Bit weird, but okay. I'll just add here. Wave. Oh, go header 3. Wave. Wave spring. Okay, so what are the uses here? So now let's look at the uses. Alright, I'm gonna add the uses. Let's add the use here. So what are the uses? The uses are medical devices. There you go. So medical devices. So implants. Okay, medical devices. Conical spring. Okay, so bevel washer was up here. Let's add some uses here. So bevel washer used in bolted joint, preload maintenance, valve assemblies, heavy machinery. I like aerospace fasteners. That sounds cool. Fasteners. Okay. So these are your uses. So let's do them in a different color. Okay. So these are your uses. Okay. We did bevel washer. Now we have rectangular section. Now flat spring. I'm guessing they're just your linear springs. Oh no, wait. I think we did flat spring here. Hold on. Helical tension, compression, leaf spring. Okay, so we have leaf spring. Where do we put leaf spring? Okay, let's put a use for leaf spring. So beam. I'm guessing the flat ones are here. Is this the flat one? The beam? Oh wait, no, I didn't mention beam. Okay. Okay, so beam is also here. But that was tension bar. So we also have a beam. Okay, cool. Let's go down here. So you have torsion coil. Yeah, okay. Leaf spring. We didn't. Is this the leaf spring? What are the uses for this? Okay, the uses are truck trailer suspension. So suspensions, and horse drawn carriages. Okay. And then we got your helicals, I'm guessing your compression ones. So this is compression coil, I'm guessing. So this is also your compression coil. Let's add some things here. We got ballpoint, ballpoints, shock absorber. Okay, and tension. This is basically your extension. Trampoline, toys, and garage doors. Okay, so these are some uses for tension. Okay, we talked about bevel. We talked about leaf, torsion bar. So let's add it here. I mean, I think we talked about bicycle wheel spokes. We talked about torsion bars, so that's okay. Flat spring, clock mechanisms. Okay, constant force spring. No. Bevel washer. Yeah, we did that. Torsion spring is okay. Gas spring. No. Okay, so I think that. Oh, torsion bar. Wait, hold on. Let's add it here. So let's add the use here. So torsion bar can be used in aircraft control surfaces, and yeah, okay, that's it. And I'm just gonna write industrial torsion loads. Alright, cool. So these are some uses. Anything else? No, I think that's it. Okay. The application, aerospace, consumer, industrial. Yeah, now at part C, we're now looking at design, detail, and calculus. Okay, so let's go over this. So we have F equals K. Okay. Load requirements. So springs must be able to handle. So, okay, let's write part C here. So over here, let's write over here. Here 2. There 2. Part C. Okay, let's part C, and this is design, details, and calculus. Alright, cool. Okay, so what are we looking at? Load requirements, space constraint, environment factor, and fatigue life. So these are the 4 things we're considering. So let's add on to here. Maybe I think this can be in just one line. So let's do this, and so we're looking at load requirements. Can handle deformation, handle static and dynamic forces forces without deformation. I think if I change this to, hold on, caption, yeah, that works. Okay, and we'll just make this bold. Okay, cool. Deformation. Next, we have control is space constraints. Okay, so it needs to fit in the available dimensions. Okay, that makes sense. Then environmental factors. So environmental factors. So consider temperature extreme, moisture, corrosive environments. So be wary of temp max stem extremas. That is not a word. Extremes. Moisture and corrosive environment. Okay, cool. Fatigue life. Design must account for repeated loading and unloading cycle. So fatigue life. Why is this even lower than the other one? Okay, fatigue life. Design must account for repeated loading, so it needs needs to withstand repeated loads and unloads. Okay. Alright, cool. Then we know it's F equals kx. Yeah, we know this part. So now this is where we have more interesting stuff. We have stresses in helical springs. Okay, so we have a force being applied here. We have D is the helix spring diameter. Small d is our wire diameter. So wire diameter is this one, and d is the spring diameter. Number of active coils, so 1, 2, 3, and so on. G is the torsion modulus, J is the polar moment, and F is active force, and D is torsion. With this, all of this combines to make this formula. Now with this, at the end of all this, you get this formula over here. We have your one. So I think for the calculations, what we need to know is this surface index here. So for surface index, the C is important because we used it in our tutorial. The C is important here. And we know the C is always, for most spring, this is always, so that's right here. It says 4C12. Okay. Stronger spring, smaller index, thicker wire, smaller outside diameter. Weaker spring, have larger index, thinner wire, and larger outside diameter. So we might be asked about this, so let's write it down. So spring. So if I want a stronger, so control stronger spring, I can do two things. I need a, let's change the color. I need a smaller index. And how do I get this? I can get this by thicker wire or smaller outer diameter. Okay. Okay, that's for stronger springs. Okay. Let's do a similar one for weaker spring. So we will have weaker spring. We have larger index. So how can we get this? We can get this by thinner wire. So just the inverse. So larger index is thinner wire, larger outer diameter. Okay. And then we know from this, and okay, so let's also mention over here that this part here. So spring index less than 4 is hard to manufacture because it might come. So let's mention this here. Let's make it a bit smaller here, and let's do it here. There we go. Okay. Then helical springs, we know that these formulas will be given to us. So this is not really an issue, to be honest. So I think this will just be given. So all we have to do is apply these formulas. So you'll be given tau max, or you'll be given the force, and we just use these formulas. And most likely you'll be given Ks, or he will tell us which K to use, and we just apply the formulas. We just go here, Ks, and boom, and we know Ks, and we just apply the formula. So that's not really an issue. Now, so direct shear across shear stress is distribution across the section. Torsion is a cross section like this. Combined chain direct shear and torsion. Effect of stress concentration on the edge. I don't think this is something that will be mentioned, to be honest. But if it is, all we need to know is across the wire, if we have a okay, let's just draw a spring here. Okay, Control C, Control V. Let's move this here. Control C, Control V. All right. And a last one over here. Okay, so let's quickly go over this. So we have this. I'm gonna just quickly go over them over here. I'm gonna draw them here, and I'm just gonna select them because I am not doing this again, or rather, am I? Yeah. Okay. Okay, yeah, okay, now they're all almost equal, so that's fine. Okay, so here here. Okay, so what's happening here? We know that we get just shear. So this is just shear. Oh no, no, that's right. Shear and torsion. Okay. Direct shear. Torsion. D plus T. Ks. So we get a normal distribution here, like this. Then we get a distribution like this. Then we get a slanted direction to the top and bottom, something like this. Then we get a line. Okay, let's do that. So we get a line like this. Okay, so we have arrows, arrows, arrows. And then again, same. So we have arrows up, arrows up, arrows up, and then arrows down. Same, arrows up, arrows up, arrows up. Okay. Okay. This is not as important. I mean, this will be given if we want. We just need this part here, the U part. The main thing here that we do need to know is yeah, this formula here, K, where, just so you know, this K is your N actual. So we're gonna use N actual here. Okay, so where do I want to put this? Okay, let's put it here. Heat compression, there are 4 types of ends. Yeah, so this is important. So plane ends have squared or closed edges. So yeah, deforming. And then we have, should always be, yeah, okay, let's write here. Let's have a text. So 4 types of, so we have plane ends, Control B. And then we have a squared or closed. And springs should always be both squared and ground for better transfer. Okay, plane ends, the most important thing about plane ends are, if you look here, is that plane ends, it's just NA. Your NA is just the same, okay? Then for plane and ground, so that's right here, so plane and ground is NA plus 1. For a squared or ground, for squared or closed, that is NA plus 2. And for squared and ground, NA plus 2. Okay. All right. We usually say that the active number of turns is 3 to 15. This isn't true in calculation, so that's not an issue. Okay, machine loop ends used. No, that's fine. Okay, no. Anything else here? I don't stress augmentation factors. I don't know what, okay. I don't know what these things are. So I'm guessing this is not coming. In designing a spring with hook end, the stress augmentation effect must be considered. So let's write here for, okay, so hook end design consideration. So you have to look at stress augmentation factors for points A and B. So then I'm pretty sure we will be given this if we are asked about this. So again, I'm not really stressed about, we shouldn't be stressed about this part here. Okay. Then we have extension spring, very similar to compression spring, except end coils are bent into the hook to apply load. Higher stresses in end hooks often govern design. Winding process produces preload that must be overcome. So I'll just add this. Bam, over here. And a picture of this is just, so we have preloads like this. Again, actually no, this is not relevant, it's fine. Now this is important because this, so if we get a value for our diameter, we need to look at our preference. Let's look at the tables, and whichever table comes first, we look at this preference first, and then the next one, then the so on. So if you get 4.9, you look at 4.8 because that's the closest. No, you look at 5 because that's the first preference after 4.9. If you got, like, let's say 3.7, you have to consider the one right after 3.5, so 3.8. Okay. Ideally, you prefer to make it 8. Okay, ideally. So just note that. Okay, end condition determining critical buckling situation. Free to tip, fixed ends. Constrained parallel, fixed ends. Critical buckling, what's the difference? So parallel ends, it's stable, unstable, and non-parallel ends, it's unstable, stable. So what this saying is that for a higher ratio of free length per diameter, it produces more stable. For lower ones, it's more stable. So there's a less deflection. So if you look here, there's less deflection. And then for parallel ends, so basically parallel ends, it's more unstable. Okay, that's what we can. It's more unstable. More unstable then. Okay. Compression. Okay. More in spring, part D, spring and stiff. So we have series and parallel. Okay. So for combining springs, so let's try over here. Part D, combining springs. We have series, where you have this. I'm gonna use just vibration terminology here. This is 1 over KEQ equals 1 over K1 plus 1 over K2 plus 1 over K3. This is K1, K2, K3 system. Okay, let's write that again. Okay. For parallel, so let's draw in parallel. So parallel will be when you have something like this. So you have a block, and then let me just change this to black. So you have K1, K2, K3. So your K equivalent will be K1 plus K2 plus K3. So combining springs. Good practice, always have a support for the spring. So again, we're going to mention this because we might be asked, what should we do to enable the spring to be better loaded onto a surface? Provide a support, okay? And okay, that's it. Let's stop here.